Okay, so this video I'm going to talk about alkaline electrolyzers, alkaline water electrolyzers, or alkaline hydrogen generators. I'm going to talk quickly about the corrosion rate of the nickel electrodes, and then I'm going to talk about the cost of producing a alkaline hydrogen generator. So starting off, I want to talk about what the current estimates are to what exactly the cost breakdown for one of these systems is. As you can see here, GE estimated that one could produce a generator of this type for around $100 a kilowatt. But what's interesting about it is if you take that cost and then you compare it to the total material contribution, so you add up the amount of nickel used, the amount of diaphragm separator used, and the gaskets, and all the other components, the end plates, you actually find that the number is a lot lower than that. So going down to the most important number that you can look at is the overall corrosion rate of the electrode, because that's going to determine how essentially the loading of the electrode. So assuming 1 square meter as a metric, you could have anywhere from 100 grams per square meter used to 400 grams. It all depends on the corrosion rate. So a typical corrosion rate, of course, the anode, the hydrogen side, will have a higher corrosion rate, typically like, let's say, 0.25 mils per year, which is about 0.006 millimeters. You can see here, this is for the anode, it's about 0.065 millimeters. For you can see the ideal is actually sort of 70% nickel. You go up to 100%, it actually slightly increases. If you go to the cathode, it's quite a bit lower. You can see it looks like about 0.02 millimeters. And essentially, the corrosion rate is the important metric, because if you take that standard rate of, let's say, mils per year, and then you compute the surface area, right, and you have the density of the material, you can calculate how much material loss there is, right? So you assume that corrosion rate is going to be 0.25, all right? So in this case, we're going to find the corrosion rate from the metal loss. So I'm going to go to grams, we put, say, 40 grams, and when we have 1 square meter, and then we have 8.9 grams per cubic centimeter, and then we have 1 year, 8,700, and you can find it's 0.17. That's a bit low, so realistically, so we put 55 grams, and we get to about 0.245. So going back to that number, which we had right here, which is 0.07 millimeters per year, and that's at, so that's a very conservative estimate. In fact, that's probably an overestimate, because you're operating in pretty severe conditions here at 117 degrees. As you can see, if you up that temperature, right, it goes up a lot higher. So you want to stay ideally like 80 C or lower. Now at 80 C, you can see it's a lot lower for a nickel alloy right here, which is about 60% nickel for the N06625. It's only 0.7 micrometer. So the corrosion rate is extremely important, because it basically determines how much material one has to use. Now, if you use, let's say, so slightly higher estimate, like for example here you had a corrosion rate, and again these numbers all sort of vary. For high grade nickel, you're going to get like 1015 per year, which is about 0.47 mils per year at 180. So 180 is quite a bit hotter than that 117 number, and again down to 80, so you get quite a lower number. So if you operated at that lower temperature, you could have a very low nickel loading of, let's say, 100 grams, because let's say you got to 0.10, right? So if you get to 0.10 mpy as a target, then let's say you have that, and there you are, 0.11, that gives you 25 grams of material lost a year for 1 square meter. If you take 10% loss a year is acceptable, you take 25 divided by 10%, you need 250 grams per square meter to achieve that loss of 10% a year. So in other words, you need at least 250 grams of electrode for 1 square meter. If you configure that in a mesh, so assuming a mesh is an effective electrode to maximize the surface area, a pretty fine mesh will give you around that number, right? So if you take typical meshes on the market you can see the mesh density right here is anywhere from 100 grams to 400 grams per meter too. That's what they abbreviate as a surface density. So anywhere from the mesh could be 50 by 50 to up to 150 by 150, with some meshes obviously being a lot thicker. But an 80 by 80 mesh is going to have about a surface density of about 200 grams per square meter. So assuming you have that type of mesh, what you're going to find is that the other thing is obviously you have to look at the ratio which you have 1 square meter of actual mesh is actually could be even higher or lower in total surface area, right? So let's say you have a mesh that's 1 square meter mesh. You might find if it's a pretty fine mesh like 100 by 100, you might find like 2.5 square meters total surface area, right? So you can't calculate the electrode surface area. It's just the mesh area. You have to look at the actual total surface area of each wire, right? Right. So that's actual. So in other words, a mesh. So an 80 by 80 mesh will weigh 0.48 kilos per cubic meter, which is about 400. It's just close to that number, but in reality, it's going to be much greater surface area, right? So if you use this conservative corrosion rate of anywhere from 0.25, say 0.3 mils per year, which by the way is a pretty realistic estimate, because there's one estimate found from a patent, from a GE patent, where they're using type 310 on the anode at 0.25 mils per year long-term corrosion rate. And remember, stainless steel 310 is 20% nickel, so chromium actually is a good alloying material with nickel. This alloy down here, you can see at 0.7, that's a nickel chromium alloy, about 40%, 50% nickel. And so if you actually look at what the N06625 alloy, so chromium is 23% and nickel is 58, and you get some molybdenum. So molybdenum and chromium is actually looks to be the ideal alloying material. Rainy nickel, so aluminum nickel, is also pretty good, but I was actually able to find good corrosion estimates for rainy nickel. So once you've figured out, once you've ascertained, or once you've surmised your corrosion rate, the second thing you move on to is cell density, right? So cell density is essentially going to determine how much of that electrode you need per kilowatt. So the lower cell density, typically the more efficient the system is, but in some cases you can push that cell density to pretty high levels and still maintain good efficiency. So there's some papers that I found. I mean, a really conservative estimate, if we go back, you see right here, for the commercial machines, are using about 9 kiloamp per square meter. So at 1.7 volts, right, 9,000 times 1.7 volts. That's 15 kilowatts per square meter of electrode area. Now, if you want to confirm that, so the electrode area, the cell current density is defined as the total electrode area. It doesn't include anything else, right? Because there's a lot of the actual surface area of the whole. I mean, it includes both the negative and positive electrode, the total surface area. So the current density is normalized to that cell area. So when they mean, cell that, say, 400 milliamp at 1.7 volts, they're talking about the electrode area. So that essentially means you can get a cell density, for anywhere from 5 to 10 kilowatt hour per meter to, which obviously means the actual nickel loading is very insignificant. That's really what this is all about, because the whole point of this video actually was to show that the Alkaline machine doesn't use a significant amount of this electrode material. And even if the electrode material were made out of platinum, for example, if you had platinum which would have a really low corrosion rate, right, in that alkaline environment, even lower than nickel. Let's say you had an ultrafine mesh, like a 150 by 150 mesh, and let's say the mesh density was what we saw there, from anywhere from 100 to 400. Let's say we took 100 per cubic meter or square meter. If you used 100 grams of platinum at the current price, around $5 a gram, so that would be $5,000 for 1 square meter. But if you could get a cell loading of, let's say 15, right, that's only $300 a kilowatt, which is close to the price, let's say, of a PEM cell or some alkaline electrolyzers right now. So I mean, obviously you're not going to use platinum. There's no need to use platinum, right? It would be a waste. But it's just an example of why the actual material cost is rather minimal, because platinum, right, is $50,000 dollars per kilogram, whereas nickel is 18, which is a factor of 2,700, right? So platinum is 2,700 times more expensive than nickel. You could, even if you used ruthenium, for example, as the electrode, it would still be rather affordable. Nickel, to get to an electrode cost of $100 a kilowatt, nickel would have to be about $1,000 a kilogram to get to. So I guess my point is that the current prices you see don't reflect the material intensity. They don't reflect the noble material intensity at all. Most of the cost is related to the small production volumes and the fact that these are really niche products, and you have you essentially have assembly costs, right? It's not reflecting the material cost at all. Whereas a battery right now, a lithium-ion battery, I've heard numbers from 50 to 70% materials. But alkaline cells, you cannot say that 50% of the cost of an alkaline cell is materials. That's not founded. That's unfounded. So assuming a cell loading of 7 kilowatt hours per square meter, let's say use half a kilo of nickel, right? Okay, so that's 0.5, and the market price of nickel is right now about $18 per kilo, but let's just give it 20. That's $10 per square meter for the nickel. Now in reality, the mesh costs more than that, right? Because assuming you don't just use like a piece of foil, right? You're actually going to use a mesh, which is stronger and better surface area. Although again, as we said, the surface area is in a way irrelevant because it just directly relates to your corrosion rates. You could have a super high surface area mesh, but it means your corrosion rate would be so high that it wouldn't be viable. So, assuming you use a mesh, the cost of the mesh is about 50% is about material, and the rest is actually fabricating the woven wire, which they just take a weaving machine and they take really fine wires and weave them. So, if you go on Alibaba and you look for meshes, the price varies a lot. But let's say you want to get a stainless steel mesh, right? To add out the cost of a mesh, you can figure out like what is a stainless steel mesh cost. And then you can adjust for the material. So you can find anywhere from $12 to $35 a square meter, 2 to 15. You got look at fine meshes, 3 to 10. And a platinum mesh, for example, would cost, $100,000 a square meter. I think I found one selling for about that price. 4 to 6. So, the actual meshing cost itself is a pretty small contributor. So assuming, the exact price that I paid was about $35 per square meter for a nickel 99.6% a nickel cobalt N6 alloy, which is what they call it. It was $33 per square meter. So assume you take that price. So 1 square meter, right, weighs 0.4 kilos, and our density. So our density is exact. So 0.4 is 1 square meter. So the density, let's say, is 1 to 1. Okay, that's easy. So the 1 square meter of actual mesh area is the same as 1 square meter of the actual total surface area of each wire. So if you take that at 35, and then you divide by 7 kilowatts, and then you're at $5 per kilowatt for the mesh. So it's still very negligible. An intermediate number would be around that, and then the cell density, if you do 300 milliamps per cubic centimeter or cubic square centimeter, then you're at 1.7. That's about 5 kilowatts per square meter. But again, these commercial systems can operate. If you can be between 5. Let's say you have 5 kiloamps per square meter. That's 5 at cell voltage. Let's say 1.6 is 8 kilowatt hours or kilowatt per square meter electrode area. So assuming, let's say 8 is a good number. I did it at 6.8 because that's my modeling showed me that was going to be the ideal efficiency. That's what we haven't gone over yet, is efficiency. But we're really assuming that you're going to be pretty close to what alkaline electrolyzers always have been, which is about 70-75%, which is anywhere from 45 to 50. So if you take these systems, you can see here at 50% load, it's 3.9 per cubic meter, which is divided by 0.082. 3.9 divided by 0.082 is 47. So 47 is a pretty typical number if you run them at 100%. And again, that's because if we assume their cell loading is up to 9, if you run it at half, so 5 times 1.6, right? It's 8. So that's why I size it at 7. So I size it even less. So if you size it to if you run at 25% load, you see you get it 3.7. So 3.77 to be exact, by 0.08 to 45, 46. So 45 at the high end, 50 at the high end. 45 at the low end, 50 at the high end. So that's a typical number. You're not going to get much below 45. It's possible with really, really low cell loading. But again, it's a trade-off. So if you have higher cell loading, it just means you need less nickel. It's less efficient. You decrease cell density, use more nickel. That's a trade-off. But again, if we found that 1 square meter mesh is $35, if you do 10 kilowatts for 1 square meter is $3.50 per kilowatt for the mesh. If you do 5, right? If you do 5, then it's 7. So it really all depends on what the person who uses the system is aiming for. If they're aiming for a high output, they just want to produce a lot of hydrogen in a compact package, then you'd want high cell loading, right? which is good. You can use less material, but you can sacrifice efficiency if you want really low. So I mean, there's some numbers where they use the term MMW, which is what the HHO guys use. It's milliliter per minute per watt. Typically, like 6 to 6.5 is achievable, but I've seen numbers up to 8. So 6.5 would be 47, 8 would be about 39, and 5 would be about 50, 55. I mean, some of these systems can use up to 70 kilowatt hours per kilogram. Some of these really small hydrogen generators for HHO generators for they're used for carbon cleaning. If you put carbon cleaning, sorry, I'm just typing one hand because I'm holding my mic. Yeah, carbon cleaning HHO. So these systems, they're pretty power intensive. You can see because again they're designing them for compactness. So this cell here is using about that would be about 60 kilowatt hours per kilogram of hydrogen per hour, which is a pretty typical number for a small cell like this. Because again, they're designing these for power density, and power density is inversely correlated with efficiency, but it's positively correlated with material intensity, or I should say, it's correlated with low material intensity. So you increase power density, you decrease material intensity, but you conversely decrease efficiency. So the optimum hydrogen generator would have high material intensity but low power density. So there's that negative relationship there between those two variables. So here we have a paper on a small dry cell. Now they had a plate area of 132 square centimeters. I just confirmed that here. So the plate area is 136 square centimeters, and the peak gas output. Now this, you can see this chart here is for constant voltage with varying current. So they're producing just about 650 milliliters of HHO gas at a current of 42 amps. Now this is figure 6. So figure 6, they say here that on figure 6 it's a constant voltage of 2 volts. And so if you take that as 84, that's a current of 42, so that's 84. And you have a gas output of about 650. So take 650 divided by 84 is 7.7 mmW. That's milliliters per minute per watt. The point here is to illustrate that at low current density, which that would be 136 square centimeters at 84 watts. So you take 84 watts divided by 136. That's 0.61 watts per square centimeter, and 1 square meter is 10,000 square centimeters. So that's 6.1 kilowatt. 6.1 kilowatts for a square meter of plate. So then if you take that chart, that's constant current, varying voltage. So figure 5 here. So it's figure 5, a constant current of 7 amps. So let's take the gas production here at the peak voltage is 10, and we said that was 7 amps, so that's 70 watts. So we said that's about 11 times 7, 77 watts. And the actual flow rate, right, is not this number up here. That's a theoretical flow rate. So the actual flow rate is the one with the square. So that's 450. So let's do that. It looks like about 11 times 7 amps. That's 77 watts. 450 divided by 77 is 5.8 mmW. That's a pretty typical number if you're at 12 volts. Now, if you go down to let's say 4 volts, that's 250 milliliters. You can see here per minute, 250 times 7, or excuse me, 4.5 times 7. That is 31 watts. So take 250 by 41 watts, 6 mmW. And then you go down further, it's, let's say 2.3 volts looks like it's about, that looks like about 150. So 3 times 7, 21 watts, 150 divided by 21. It's about 7. Yeah, so the lower your voltage, the higher the efficiency. So the reason why a lot of these small cells get poor efficiency is because they're running at at 12 volts. You don't want to be at those higher voltage levels, which is why you use those neutral plates to get the voltage down. But you know that this cell is actually including all these neutral plates. So that actually they're running 2 volts into the cell, including the 4 or 5 neutral plates. Their actual voltage at each plate is substantially lower than that, which is the theoretical overpotential is quite a low voltage. So then you can see here they're also using pretty low concentrations of electrolyte. It's only, for this is 5% NaOH, which is sodium hydroxide. Often the commercial alkaline machines are using KOH, potassium hydroxide. But so I guess the point of this is to illustrate that you can get much better efficiencies at lower power density, which, and again, this paper is published in Fuel, which is a pretty good journal, so you're not going to get garbage in there. Which, you know, there's a lot of guys out there claiming, you know, like efficiency that's impossible to believe, right? You can't get below Faradic efficiency, which is 35 kilowatt hours per kilogram. That's the theoretical minimum. So you can get to 40. 40 is a believable number, but anything below 40 is pretty hard to get. So yeah, there's really 3 major variables. You got the corrosion rate, the cell loading, and then the efficiency. But the most important number is the corrosion rate, because the corrosion rate is what determines just how fine a mesh you can use, essentially. Because there's a paper out there, the microfibrous alkaline wall electrolyzer, and they were getting power densities 12 to 50 times greater than conventional PEM or alkaline machines by using very, very high surface area, ultrafine, what they call a foam electrode, which is just a very, very fine mesh. So, you know, and they actually found rather minimal degradation, which is surprising, because if you have such a high surface area, imagine the mass of material is so low compared to the surface area, corrosion is going to be extremely high. So, you know, imagine you have a loading of 100 grams per square meter. Well, if you did, and your corrosion rate was let's say your corrosion rate was 0.2, right? We'll go back to 50 grams, which is about 0.2. If you had 2 square meters, that doubles the corrosion rate to or it has a corrosion rate. So that would mean that at 0.2 MPY at 1 square meter, you would end up losing, if you had 100 grams, right? You'd end up losing 50% of the electrode in 1 year, which is unacceptable. You can't lose so much. So ideally you want to be like, you know, at 10%, so that's 500 grams. So that's why that number 500 grams is pretty typical. Now, if you double your corrosion rate to 0.4, then 500 grams turns into, you know, 20% a year. You want to get to you know, about 0.2 MPY, which is possible. That is very, very possible. In fact, it's not possible. That is what you will find on these machines. Because as I went to, we go back to that number, which I have right here for the anode. You can see here that is about looks to me like that's. I actually added that up exactly with a ruler. It's 0.7. 0.07 millimeters, which is about 0.25, 0.3. So it's very, and again, those are at conditions that are harsher than what we would like to use, because if I go back to that paper on that dry cell, you find that they're only using 5%, and they're only at their peak temperature is 50, so or just a little over 50. So it's very possible to design a cell for lower power density, higher efficiency, longer life, and achieve those three targets. You want to use less electrolyte, you have less corrosion, and you also want to use a lower temperature as well as a lower cell loading. So obviously you run more current through that electrode, you're going to create more heat, and so the heat is really related directly to the power density. So then the I guess the final thing would be what's going to happen to the market price of this essential element for our electrolyzer, which is going to be your elemental nickel. If you look at the long-term price, it peaked in 2007 at $50 per kilogram. That was with tremendous demand growth from China for stainless steel primarily. A lot of people are projecting all these electric cars using nickel, but those are very optimistic predictions. And in reality, batteries right now use less than 1%. So it's not really a huge concern. I think the most important factor here, it really is the reducing the loading of the material as much as possible, and subsequently reducing the cost, because it's feasible to produce one of these hydrogen generators, alkaline hydrogen generators, for $30 a kilowatt, and that's really what we're shooting for. So we're trying to get these systems to market. I have a customer right now, so it's possible to get this machine to market using this methodology, which is COTS, which is commercial off the shelf. Now, this is actually what SpaceX used to reduce the launch costs from $10,000 a kilogram with the space shuttle down to about $900 a kilogram for the Falcon X. So you can do this; it's possible, right? And as long as materials are not working against you, right? Like you're reliant on, I don't know, palladium or platinum or something like that, and then you're screwed. But if you're relying on a material that's relatively cheap, you don't need to use much of it, which is in our case, then you're in really good shape. So it makes a lot more sense to produce hydrogen and to produce carbon fiber to store the hydrogen for mobility than it is to use gargantuan amounts of cobalt, nickel, and lithium and other assorted elements to build a battery economy. So, but anyway, so that's the main point here, is that $30 a kilowatt is possible. So one final thing is even if we get to the point where nickel is a lot more expensive and we might not want to use it, although I think that's very unlikely to happen. It's probably not going to reach its $50 per kilo price. It did in 2007 for a long time. But even if it does, we added up that if we use 500 grams per square meter, let's say $100, right? Let's say it goes to 100, so twice what it was in 2007, which again is unlikely. But let's say we do, it's $50 per square meter divided by, and let's say divided by 7, that's still $7 per kilowatt. So again, it's going to take a very expensive nickel to reach even $100 a kilowatt, which it basically is impossible. I mean, it won't. Nickel Institute estimates we have 300 million tons. So again, if you don't believe me, it's Nickel Institute says there's 300 million tons on onshore, and then there's another 290 million tons in the ocean. So it's not a problem, right? It's not platinum. I think there's total reserves of platinum are 50,000 tons. So 50,000 versus 290 million, that is 0.00017%. So it's never going to become platinum, right? It's not possible. It's just so much more abundant in the crust. So what I wanted to show you here was a corrosion rate estimate for carbon steel. So if you run carbon steel at 60 degrees, the corrosion rate is 7.5 UM per year, 0.07. It's 0.27 mils. So if you got to, if say for whatever reason, and this is a pretty good paper here that from the National Association of Corrosion Engineering, I think. But anyway, this paper is from Norway, so these guys know what they're talking about. I mean, it's a serious paper. It's actually the best paper I have on corrosion rates. I probably shouldn't be putting this on YouTube, but what I wanted to show you is that you can see here. So this is for the carbon steel. Still looking pretty good. The nickel, which is down. Where's the nickel? There's the nickel. And you can see it looks very, very good after I think this was 35 days at 80 degrees. Yeah, I think it was 35 days. So if you go back to nickel at that rate, you can see at 80 degrees, the nickel rate is basically negligible. So if this is correct, and you can expect a corrosion rate of, they didn't say whether it's the anode, this is the anode or the cathode. I mean, I assume they account for that. But if that's true, then you can expect, so 35 days, and so 30 bar, 25% KOH, and they don't say what the current density was, but I don't think it really matters what the current density was. If that's true, 0.7 UM, so that is 0.0007. So let's go back to micrometer. 0.7 is 0.02. So let's bring up our little corrosion calculator again, right? So let's assume we have a loading of, so one square meter. Say we have a corrosion rate of 10 grams. 10 grams. So that would be like so we're solving for MPY, right? We don't use MPY and get the loss. 700 hours. So 0.04. So what do we say again? Let's said it was 0.02, right? It was 0.02. So we would be able to have a loading of 100 grams if that number is right. And 100 grams would mean corrosion rate at temps in a year, and 100 grams would mean 0.10 times 20. $2 of nickel per square meter divided by 7. It's 28 cents. I mean, this is amazing, right? And no one is really talking about this. I mean, this is kind of amazing. I just sort of stumbled upon this because I've been working on hydrogen for a long time now, and I always assumed, these things cost $100 a kilowatt to make, right? It's got to be, right? It's got to be the material loading. I always thought they were using like kilos of nickel per square meter, but that's really not the case. There's no need to use that much. And anyway, if this is right, you just use carbon steel, and carbon steel is cheap, right? I mean, even though iron prices have doubled this year, it's, I think iron ore prices are like $200 a ton. So I don't think we're gonna have a problem of running out of iron. So you could just make an electrolyzer that's a modular design. It's easy to take apart and just pull those plates off every 6 months or so, right? Just replace them and just use cheap iron. I mean, labor costs are a factor, right? So I didn't estimate what the labor cost would be to assemble one of these cells. I assume you could just probably have a robot doing it, because you're just laying on a sheet of metal, then you're putting on a gasket, and you're putting on another sheet of metal. These people make these things at home, right? And that's one thing to emphasize, is that you can't make a battery at home. You can't make a lithium-ion battery, but you can make a hydrogen generator. Anyone could. So I think we're leaving off on a very positive note, which is that the material intensity of this technology is really low, and we could have billions of these little machines on every solar farm, and people could have these to store renewable energy. They can use them to produce ammonia, and that opens up a whole opportunity to produce ammonia for farmers, which we're also working on. I guess my next video is going to be on that.
All right, so there's effectively two ways you can build an alkaline electrolyzer, or any electrolyzer for that matter. There's a monopolar and unipolar cell configuration. So a unipolar cell is where you have current going into each electrode. And in a bipolar cell, you have current passing through the first set of electrodes, or the first electrode for that matter, and that could be the positive and negative, and it exits at the final electrode. So if those familiar with dry cells or HHO cells, you'll notice that they call them neutral plates. That's actually not technically the right term, because in an electrolyzer, a commercial scale electrolyzer, most of the electrodes are what they abbreviate neutral plates, which they're not really neutral because current's still passing through them, and if current passes through each electrode, it forms an anode and a cathode on actually each side of that electrode. So if you imagine most alkaline electrolyzers that I'm aware of use a bipolar cell configuration. So you can see here, you got the current coming in, but it's not attached, right, to each electrode. So you don't have a positive, right, attached at the end of this electrode and a negative attached at this electrode. It passes through the electrolyte medium. So in this case, you would have, for example, if you had a let me find it. Yeah, if you had 250 electrolysis cells, which each cell is an electrode, a negative, positive electrode, and a diaphragm separator. You're going to have 300 volts to 550 volts. So obviously you can't connect that 350 volts right to each electrode, because then the 350 volts would be, each electrode would be receiving 350 volts. That's obviously way too much. So you divide the total voltage by the number of cells to get the cell voltage. So in the case of a unipolar cell, you actually have to have the voltage coming in at each electrode at that exact voltage, right? Because there's no reducing effect. So each time you have so there's actually a really good video by an HHO guy on YouTube where he explains this. So if you hook up the current on one plate, and then you hook up the current on the other plate, so this would be the positive, let's say this would be the negative at the other end. Let's say you have 12 volts across this entire electrode. In reality, between each cell, you might only have 2 volts. But that cell in the middle is still receiving current, right? It's energized. But each time current flow, because you see, there's no connection between two electrode plates. If you have a connection, then by definition it can't be an electrode, right? It's going to be one electrode. See, they're not all stacked up against each other and connected. That would defeat the purpose. The current is actually passing through the electrolyte medium, so that's the alkaline water, and jumping from one electrode to the other, forming an anode and a cathode each time it does that. So in each progressive stepping of the current, so each time the current passes from one electrode to another, it forms an anode and a cathode, and that's what they call a unipolar cell. All commercial machines use that configuration. So you can see this one, for example, is using this configuration where you don't have current attached to each one. You have the current going through, let's say, 12 cells, 50 cells, 100 cells, depending on the number. If we can find, you can always find. Yeah, here's another one of these machines. You can see there that little piece sticking out at the bottom is where the current would go in. So you can see there the current's coming in. So yeah, that looks like, so that's on the left hand side you have, looks to be that it's red in the middle, so that's probably the positive. So current's coming in there, and then it's going to exit at the left side. So yeah, if that, yeah, you can see there, current's coming in on those little flanges at the side sticking out. Now, essentially the reason you have to do this is because if you imagine, if you have, you can't provide 2 volts, right? There's no power supply in existence that can take, because most electrolyzers actually, they even if they're running off a solar farm, they convert from AC first, and so they feed into the AC mains and then they rectify back to DC, typically about, again, depending on the size of the electrolyzer, anywhere from 50 volts to 250 volts. I mean, most electrolyzers on the market right now are operating from between those voltage ranges. It's just not practical to provide, because it's possible you could have on each of these cells, right? You could have a positive coming in and a negative coming in, and you can do that, but you'd have to have 2 volts or 1.7 volts, and that just wouldn't be practical. So I want to talk quickly about membranes now. So one thing that's really nice about the COTS methodology is that we can actually use currently available materials, synthetic membranes, that are not the zircon-based systems, which are of course much more expensive since they're only made by one company. They have patents on them. They have intellectual property. You can't just go on Alibaba and buy this technology. What we've found is the polyether sulfone ultrafiltration membrane, which is it's been used on electrolyzers before successfully. There was an experimental electrolyzer built in this paper here, and they actually use these. And what's great about this is that, again, since we're doing the COTS system, you can actually buy the polyether sulfone membrane, and it's a commercially available product, and it actually performs very well. So here's actually the product that I bought. It's got a pore size. They say here the pore size is 0.2 um. I had a 0.2 pore size as well. This guy sold me pore size 0.10 to 0.3. I think I got 0.10. Storage hydrophilic, so that's what we want. Water will pass through it. These are actually used for water purification. Okay, and they're ionically conductive, right? So they'll let the ions flow through. You can run them wide range of pH values. You can operate these at up to, I think I saw 80 C, which is a good temperature range. It may not have the durability of the Zirfon system. I'm not claiming it does. It probably won't, but it's a much lower cost solution if you wanted to build an alkaline cell off the shelf, right? And that's the whole point of this video. Actually, it's not really a technical elaboration of alkaline technology, because we're very familiar with the technology. There's everything that's been said about this technology has already been said, right? The point of this video is really to illustrate that we can reduce the cost by using off-the-shelf components, and we can make these systems for $38 a kilowatt. That was really what this is about, right? I mean, if you want to learn about electrolyzers, you can just find a book. There's a whole textbook on it, right? And so, people say, well, the materials are not ideal. They're close to ideal. Okay, they're close to ideal. I mean, maybe Zirfon is ultimately ideal, but it's going to cost 4 or 5 times more. I mean, I haven't gotten a quote for it, but this cost me $10 per square meter for a 200 micrometer. Okay, so 200 micrometer, it was $10 a square foot, which is very cheap. I do not expect the Zirfon to be even in that ballpark. It's probably over $100 per square meter. Excuse me. So it just makes a lot more sense to use these systems, off-the-shelf components. And again, I'm not the only one who says you can use this, and it's not a claim out of thin air. You can use these things; they work. And so that's the point, is that we can build these systems for a lot less than they currently sell for by using this methodology, which is what has been used successfully to reduce the cost of a lot of other highly specialized products. We've already mentioned that. So there's a lot of opportunity to bring electrolyzers to market for a lot less than they sell for currently. And that's going to enable low-cost hydrogen that can then be used to produce low-cost green ammonia, and eventually pave the way for an ammonia transportation economy, which is really what we're aiming for, as we went over in the previous video. So I hope this could be of use to people who are trying to look at hydrogen ammonia solutions for a future low carbon economy. Now, one thing is to be said, we're going to have a video coming up on small scale ammonia plants, which I'm sure I'm going to get some heat on that because people say, oh, you can't scale down the Haber-Bosch, but we're going to go over that in the next video. So should be interesting.
So something quite interesting happens with the kinetics of nickel corrosion. So what you find is that pure nickel actually corrodes at a higher rate than chromium ferrous alloys of nickel. So for a alloy 800, which you can see here is a alloy 800 is Alkaline 800. It's about 30% nickel. I think about 20% chromium, the balance iron. So you find that obviously the corrosion rate for this alloy 800 is substantially lower than for the alloy 600 and the 304 and the 310. But what you find more interesting is compared to pure nickel. So there you have pure nickel up way high here and 800 all the way down here, right? So obviously something's going on here. What's going on is the kinetics of this reaction. So the presence of too few dissolved iron ions or sufficient content of silicate through at a insufficient concentration, nickel is in a passive state. So when you're in a passive state, the corrosion rate is 1 UM. So, which is why the first study we went to actually was quite accurate. So this was a Inconel 625. This is Inconel 625, 0.7 at EDC. So in their case, if you go to you find that the 600 is actually higher. 600 is actually quite poor. I think there's quite a bit of nickel in 600. It's over 60%, or just around 55%. But the really good news is that one UM per year, and if you're in the active zone, insanely high corrosion, right? So the inhibiting effect of the iron and silicate ions is due to the incorporation of these elements into the oxide layer and to change into a change of the nature of the nickel oxide. So the oxide layer is predominantly NiO and nickel hydroxide. So the nickel corrosion is inhibited when the oxide layer contains a sufficient amount of iron